Today's new topic, write Ohm's law and unit of resistance. Now Ohm's law is very common for you. You have studied under the fixed physical condition, a current flowing through the conductor, that is I, and potential difference V between the two ends of the conductor are directly proportional to each other. It means that if you increase the value of voltage, then current also increases through the conductor, and vice versa. If you decrease it, then current also decreases. Or we can say voltage is proportional to electric current. Okay, so we can write V proportional to I. Okay, you can see here V proportional to I. And if you remove the proportionality, then a constant is kept, so V is equal to IR, or we can say R is equal to V upon I. Okay, so this is Ohm's law that you should remember. Okay, then here the constant of proportionality is R, which is known as resistance of the conductor, and as you know its unit is ohm. Okay, this you have studied. Okay, so ohm is the unit of resistance, and if you derive its dimensional formula, then it is MLTA. Okay, M1 L2 T minus 3 A minus 2. Okay, so you should remember this. Okay, now R is depending on the material of the conductor and on the dimensions of the conductor. Okay, that is the next topic. Here R is depending on which type of material you are using, or we can say if you have aluminum wire of same length and cross sectional area that of copper wire. Okay, means both the wires are made up of, one is made up of aluminum, the other one is made up of copper. And if length and cross sectional area of both are kept same, then also the resistance will be different for both the wires, because it depends on the material of the conductor, and it also depends on dimensions, that is length and cross sectional area of the conductor. That is a later topic. Okay, here it is. What is electrical resistance? How does it depend on dimensions of the conductor? Explain. Or it can be asked, derive R is equal to rho L upon A. This is a new symbol. Okay, that is rho, which is known as resistivity or specific resistance of the given material. Okay, now as you know that the resistance means the ability to resist the flow of electric charge by the conductor is called the electrical resistance. This is a very common understanding, that the ability to resist the flow of electric charge by the conductor is known as electrical resistance. Okay, now as you know that R is equal to V upon I. Now here there is one figure which I am showing it here. Okay, this is the first figure. Okay, in which you have a conductor whose length is L and its cross sectional area is A. Okay, so here we have this first figure shows that the conducting slab, which is having length L and cross sectional area capital A. Okay, now consider the same size slab which is shown in this figure B, which is kept side by side. Okay, one is having length and area A, then similar slab of length L and area A is kept close to the first one, which is shown here in this figure number B. Okay, this is the figure in which it is shown. Okay, so here total length of the combination will become 2L. This is the total length of the combination. Okay, so the length of the combination becomes 2L. Now if you try to understand, if current is flowing through the combination, okay, then the current through this combination is going to remain same. Okay, the current flowing through the combination is the same as that flowing through the either of the slab. So the combination is having the same current, but try to understand that if the voltage across the first was V, then if next is kept close to it, then voltage across that also becomes V. So total voltage will become 2 times V. Okay, so that part we try to understand. Okay, current flowing through the combination is same, but now the voltage, barabar, if V is the potential difference across the end of the first slab, then V is also the potential difference across the end of the second slab. So what will happen, as the second slab is same as that of the first slab, current will flow, that is equal to I, means current through both the slabs will be I only. Okay, if you have the first slab and the current is I, if you place the next slab close to it whose length is same, its area is same, okay, then current through this will also be I. But what will happen, the voltage across first was V, voltage across second was, or rather say it is V, then total voltage across this combination will be equal to 2V. So earlier current was I, right now also the current is I, but voltage, that is potential difference across the ends of this combination, is the sum of the potential differences across the two individual slabs. Therefore the total potential across this combination will be equal to 2V. Okay, so the resistance of this combination, that is say RC, RC is the resistance of combination, that is equal to, R is equal to voltage upon current, but now voltage is how much, 2V, so 2V upon I. Okay, so V upon I is nothing, R. Okay, V upon I is equal to R that we have written in the first equation, so it becomes 2 times R. Okay, so the resistance of this combination, that is RC, will become 2V upon I, that is equal to 2R. So you can understand that as the length increases, its resistance also increases. Is its length becomes double, then the resistance also becomes double. Okay, resistance also becomes double. So we can say that resistance is directly proportional to length. If you increase the length, then resistance increases. This is our third equation. Try to remember this. Okay, now we have, say, let us divide the slab into two by cutting it lengthwise, so that slab can be considered as combination of two identical slabs of length L, but each having a cross sectional area of A by 2. It means that now you are cutting the slab. Okay, say for example you have, this is the slab, okay, whose length is L, but if you cut this from here, then the upper part, okay, the upper part will be having length L, but the cross-sectional area will be A by 2. Earlier the whole area is A, but the upper part will have area A by 2, lower part will also have the area A by 2, which is shown in the next figure. Try to look at that figure also. Okay, just try to understand this. Okay, the slab which was having area A is now cut into two pieces of area A by 2, length is kept the same. Now if you join here the battery, okay, then voltage across each, that is say V, voltage across both the slabs, voltage across both the slabs will be same. But if earlier in one slab if the current was I, now the current will be divided into two equal parts, one that is I by 2 in the upper slab and I by 2 in the lower slab. So voltage remains same and current is divided into two parts, that is I by 2 on the upper from the upper slab and I by 2 from the lower slab. Okay, this is denoted or shown in the next topic, or rather next point, that if it is divided into two, okay, then the current is divided into two parts, that is I by 2, but the voltage remains same. So for a given voltage V across the slab, the current through the entire slab earlier was I. In the beginning, if you try to understand, if you had the entire slab of area A, only one slab, then whole current was passing through that particular slab and that current was how much? It was I. Now it is divided into two parts, that is I by 2, but the potential difference will remains the same. Voltage across each slab is going to remain same. Okay, so now resistance of one slab, okay, either upper or lower, any one slab, that is say RL. Okay, if you divide its area, try to understand, if you divide the area of our original slab whose area earlier was A, now it has made A by 2, so the new slab which is having length L but area A by 2, then what happens to its resistance? Then resistance of one slab, either upper or lower, that is RL, say for example it is RL, then that resistance RL will be voltage upon current. Voltage is same, that is V, but now the current has been divided into two parts, that is I by 2 and I by 2, so current in one slab will be I by 2, so RL, that is R is equal to V upon I. Instead of I we have to write I by 2. Okay, so 2 will go in the numerator, so this will become RL is equal to, okay, 2 will go in the numerator, so it becomes 2V upon I, and V upon I is nothing but R. So we can write resistance of one of the slab is 2R. So we can say if the area is made half, try to understand, if area is made half, its resistance is doubled. So we can say that the area of cross section and resistance of the conductor, they are inversely proportional to each other. If area is made half, area is decreased, then resistance increases. It means they are in inverse proportion. Okay, so If area of cross section is made half, doubles the resistance. Try to understand, area of cross section is made half, it doubles the resistance. Okay, in general, the resistance is found to be inversely proportional to the cross sectional area. Okay, so we can say that resistance is inversely proportional to area. Earlier we found that resistance is directly proportional to L. Now if both the things are combined together, then we can say resistance is directly proportional to length and inversely proportional to area. So if you remove this proportionality, then resistance is equal to one constant we have to keep, rho L upon A, where rho is called the specific resistance or resistivity. Okay, so we can say that R is proportional to 1 upon A. Okay, from third equation we had R proportional to L. Here in fourth equation we got R proportional to 1 upon A. So if you combine them, then resistance is directly proportional to length and inversely proportional to area. So if you remove this proportionality and then you put a constant, then it is resistivity rho, where rho is a constant of proportionality. Okay, which depends on the material of the conductor. Try to understand, it depends on the material of the conductor but not on the dimensions. Rho is depending on the type of material, resistance depends on dimensions. Rho is same for one material. Okay, if copper is having one particular value of rho, then it remains the same. It does not depend on the dimensions of the conductor, but definitely resistance is depending upon the dimensions of the conductor. More the length, more the resistance, thicker the wire, less the resistance. જાડો વાયર હોય તો રેઝિસ્ટન્સ ઓછો થશે. Okay, if you have a larger door and if you want to say pass 50 people, then if larger door, more the cross section, they can move easily, means resistance will be less. If you have smaller door or a gate, then if you want to pass these 50 people through that door, then it would be a difficult task or there will be a more resistance. Okay, and this constant which we have introduced, that is rho, which is called the resistivity of the material. Okay, try to watch this 2-3 times and learn the theory. Okay, thank you.